Imagine boarding a spacecraft, traveling at 38,000 miles per hour, the fastest sustained speed any human-built object has ever maintained on an interstellar trajectory. You launch today. You aim straight for the opposite edge of the Milky Way. You will not arrive for nearly 2 billion years, not 2,000, not 2 million, 2 billion. By the time your ship crosses the galaxy, our sun will have swollen enough to boil the oceans away and render Earth a scorched, lifeless rock. Every continent will have been rearranged. Every trace of human civilization will have been erased by geological forces many times over. And here is the part that should unsettle you most. The Milky Way is not even close to the largest galaxies in the universe. Some are 10 or 20 times wider. This is what it actually costs to cross your own home. If you enjoy having your sense of scale permanently broken, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives, and I appreciate every single one of you. Now, let's begin. You already have a picture of the Milky Way in your head. Everyone does. It is that elegant spiral you have seen 1,000 times on posters, in documentaries, in textbook diagrams. A pinwheel of white and blue light sitting against a black background, with a neat label pointing to a tiny dot somewhere along one of the outer arms that says, "You are here." The image is beautiful. It is comforting. It is also one of the most dangerously misleading pictures in all of science. Not because it is factually wrong. The Milky Way is indeed a spiral. We are indeed located in the outer arms. But the image creates an illusion so powerful that almost nobody recognizes it as an illusion. It makes the galaxy look like something you could hold, something you could cross, something you could wrap your mind around the way you wrap your mind around a country or a continent. You look at that spiral diagram and you think, I know where I live. I understand the shape of my cosmic neighborhood. The distance from one side to the other looks manageable. It looks like a map. And maps, by definition, are things you can traverse. That instinct is wrong. Not slightly wrong. Catastrophically wrong. The Milky Way is not a map you live inside. It is a physical object whose diameter would take light itself 100 millennia to cross. And the first step toward understanding why it would take so absurdly long to travel from one side to the other is understanding what this galaxy actually is, not as a diagram, not as a poster, but as a three-dimensional object made of matter, energy, gravity, and distances that break every intuitive tool your brain possesses. Let us start with the basics. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure of densely packed stars running through its core, with sweeping spiral arms curving outward from the ends of that bar. It contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is itself staggering. We are not sure whether our galaxy contains 100 billion stars or 4 times that many. The difference between the low estimate and the high estimate is 300 billion stars, a margin of error larger than most galaxies in the universe. And we are not talking about distant, poorly observed galaxies here. We are talking about the galaxy we live in, the one we have been studying for centuries. We still cannot agree on how many stars it holds to within a factor of 4. The reason for this uncertainty is simple and humbling. We are trying to measure the galaxy from inside it. Picture standing in the middle of a dense forest and being asked to count every tree. You can see the ones nearby clearly. You can estimate the ones a little farther away. But beyond a certain distance, the trunks overlap, the canopy blocks your view, and you cannot tell whether there are 1,000 trees ahead of you or 10,000. Dust clouds, gas lanes, and the sheer density of stars near the galactic center block our view of enormous sections of our own galaxy. We are embedded in the structure we are trying to measure, and that makes everything harder. The stellar disk of the Milky Way, the flat pancake-shaped region where the vast majority of stars reside, spans approximately 100,000 light-years from edge to edge. Some recent studies using chemical analysis of distant stars have argued that the disk may extend even farther, perhaps out to 160,000 or even 200,000 light-years when you include faint outer populations and warped edges. But the commonly cited figure, the one supported by the broadest range of measurements, remains approximately 100,000 light-years for the main visible disk. That is the number we will use as our baseline. That is what crossing the Milky Way means in this story, travelling from one edge of that stellar disk to the other, straight through the centre, a journey of roughly 100,000 light-years. Now, 100,000 light-years is a phrase that rolls off the tongue so easily it almost sounds tame. Astronomy has a way of numbing you to enormous numbers. You hear billion and trillion and light-year so often that they start to feel like wallpaper, background noise. So let us stop and actually unpack what 100,000 light-years means in physical terms. A single light-year is the distance that light travels in 1 year, moving at 186,000 miles per second. Not per hour, per second. In 1 second, a beam of light covers a distance that would take a commercial airplane roughly 14 days to fly. In 1 minute, light travels more than 11 million miles. In 1 hour, it crosses 670 million miles. By the end of a full year, light has travelled approximately 5,878,000,000,000 miles. That is 1 light year. Now multiply that by 100,000. The diameter of the Milky Way works out to roughly 588 quadrillion miles. Written numerically, that is an 18-digit number, a figure so long it would not fit on a standard calculator display. The number is so large that it ceases to function as information. Your brain receives it the same way it receives a random string of digits. It does not land. It does not connect to anything you have experienced. And that is precisely the problem. You cannot feel the size of the galaxy by hearing a number. You can only feel it by comparing it to things you already understand. We will do that shortly. But for now, the critical point is this. The Milky Way is not a picture on a wall. It is a physical object nearly 600 quadrillion miles across. And when we talk about crossing it, we are talking about traversing every single one of those miles. The disk itself is remarkably thin compared to its width. At the location of our Sun, the disk is roughly 1,000 light-years thick. That is a ratio of width to height of about 100 to 1. If you scaled the Milky Way down to the size of a dinner plate, the plate would be barely 1/10 of an inch thick, thinner than a stack of 3 credit cards. The galaxy is extraordinarily flat. We live in a galaxy that is essentially flat, a vast cosmic frisbee spinning through space. The central bulge is thicker, roughly 10,000 light-years in diameter, swelling around the core like a slight bump at the centre of the disk. And at the very heart of that bulge sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million suns compressed into a region smaller than the orbit of Mercury. Everything in the galaxy, all 400 billion stars if we accept the higher estimate, orbits around this gravitational anchor. Our own Sun completes one full orbit roughly every 230 million years. Astronomers call this period a galactic year. In the entire history of Earth, our planet has completed only about 20 orbits around the galactic centre. The dinosaurs went extinct less than 1 galactic year ago, but the disk and the bulge are only the visible portion of the galaxy. Beyond the bright spiral arms stretches an enormous spherical halo of old stars, globular clusters, and most importantly, dark matter. This halo extends far beyond the visible disk. Recent research using the orbits of satellite galaxies has placed the outer edge of the Milky Way's gravitational influence at approximately 950,000 light-years from the galactic centre. That is a total diameter of roughly 1.9 million light-years when you include the full dark matter halo. The visible galaxy, the part you see in photographs and diagrams, represents a relatively small luminous core sitting inside a vastly larger invisible structure. The dark matter halo contains approximately 10 times more mass than all the visible stars, gas and dust combined. This invisible scaffolding holds everything together. Without it, the galaxy would fly apart. Stars in the outer disk orbit far too quickly to be held by the gravity of visible matter alone. Something massive and unseen provides the additional gravitational pull. That something is dark matter, and it extends the true boundary of the Milky Way far beyond the edges of any poster you have ever seen. For the purposes of this script, however, we are focused on the stellar disk. 100,000 light-years. That is the journey. That is the crossing. And understanding what that crossing actually entails requires looking at what fills the space between one edge of the galaxy and the other. The Milky Way is not a uniform slab of stars. It has structure. Complex, layered, dynamic structure. The spiral arms are the most obvious feature. Our galaxy has 4 major spiral arms: the Scutum Centaurus arm, the Perseus arm, the Sagittarius arm, and the Norma arm, along with several smaller spurs and branches. Our solar system sits on the inner edge of a minor structure called the Orion arm, sometimes called the Orion spur, which branches off between the Sagittarius and Perseus arms. The spiral arms are not solid walls of stars. They are density waves, regions where gas and dust are compressed by gravitational interactions, triggering intense bursts of star formation. The bright blue stars that make the arms visible are young, massive, and short-lived. They are born in the arms, burn fiercely for a few million years, and die before they ever leave. The arms glow because they are factories, constantly producing new stars from raw material. Between the spiral arms lie interarm regions. These are not empty. They contain older, dimmer stars, scattered gas clouds, and vast stretches of relatively quiet space. Crossing the galaxy would mean passing through multiple arm and interarm transitions, each spanning thousands of light-years. You would traverse regions of intense star formation where radiation and stellar winds create hostile environments, and you would pass through calmer stretches where stars drift in relative isolation. As you approach the galactic center, conditions would change dramatically. The density of stars increases sharply. Within the central few thousand light-years, stars are packed hundreds or thousands of times more tightly than they are in our neighborhood. The gravitational environment becomes chaotic. Stars swing around the supermassive black hole on tight, fast orbits. Some stars in the galactic center region move at speeds exceeding 10 million miles per hour, whipping around Sagittarius A star in orbits that take only a few years to complete. The radiation environment is extreme. X-ray emissions, gamma-ray bursts from high-energy processes, and intense magnetic fields make the galactic center one of the most energetic and violent regions in the entire galaxy. Crossing through it would not be a gentle flyby. It would be a passage through a gravitational and radiological storm. Beyond the center, you would enter the far side of the galaxy, a region we know even less about than our own neighborhood. Dust lanes near the galactic plane block visible light from reaching us, making it extremely difficult to study stars and structures on the opposite side. Infrared and radio telescopes can peer through some of this obscuration, and the Gaia Space Observatory has mapped the positions and motions of nearly 2 billion stars with unprecedented precision. But even with Gaia's extraordinary dataset, our knowledge of the far side remains fragmentary. There are entire spiral arm segments on the opposite half of the galaxy that we can barely resolve. Crossing the Milky Way would mean traversing regions that are not just distant but genuinely unknown. Unmapped territories that no human instrument has fully characterized. This is the physical reality of what crossing the galaxy means. It is not drawing a line on a diagram. It is traveling through a three-dimensional structure containing hundreds of billions of stars, trillions of planets, vast clouds of molecular hydrogen, lanes of interstellar dust, regions of scorching radiation, gravitational wells that can warp space-time, and stretches of near-perfect vacuum where the nearest star might be several light-years away. And all of this is spinning. The entire disk rotates. Different parts rotate at different speeds. Stars closer to the center orbit faster than stars farther out. The galaxy is not a static object you can simply fly across in a straight line. It is a dynamic, rotating, evolving system, and any journey through it would need to account for the fact that the destination is moving while you travel toward it. Now, here is where the first crack in human intuition appears. Most people, when they hear that the Milky Way is 100,000 light-years across, process that fact in roughly the same mental category as hearing that the Pacific Ocean is 12,000 miles wide, or that the distance from Earth to Mars averages about 140 million miles. Large numbers. Impressive numbers, but numbers that feel like they belong on the same scale, just at different magnitudes. Your brain files them all under really far and moves on. This is a mistake. These distances do not belong on the same scale. They do not belong on adjacent scales. They do not even belong in the same conversation. The distance across the Milky Way is not merely bigger than the distance from Earth to Mars, the way a skyscraper is bigger than a house. The relationship is more like the difference between a single drop of water and the entire Atlantic Ocean. The Pacific Ocean is large by human standards, but a beam of light crosses it in about 1/15 of a second. The distance from Earth to Mars takes light between 3 and 22 minutes depending on orbital positions. The distance across the Milky Way takes light 100,000 years. 100,000 years. You go from fractions of a second to minutes to a span of time longer than all of recorded human civilization, and you are still inside the same galaxy. The jumps between these scales are so enormous that your brain's instinct to group them together as big distances actively prevents you from comprehending the true situation. They are not points on a single ruler. They are completely different categories of reality. This categorical confusion is the single biggest obstacle to understanding galactic travel times. When people hear that it would take an extraordinarily long time to cross the Milky Way, they nod and think, well, yes, space is big, but they do not feel the actual magnitude because their brains are quietly sorting 100,000 light-years into the same mental drawer as 140 million miles to Mars. Those two distances have almost nothing in common, and until you forcibly separate them in your mind, until you build a ladder of comparisons that shows you exactly how each step dwarfs the one before it, you cannot begin to grasp what galactic distance truly means. Here is one way to begin separating them. Light travels from the Earth to the Moon in about 1.25 seconds. That is a distance of roughly 239,000 miles. A manned spacecraft can cover that gap in about 3 days. Humanity has actually done this. We sent people to the Moon and brought them back alive. It is an achievable distance. Now step outward. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. That is 93 million miles. We have sent robotic probes to the Sun's vicinity. The Parker Solar Probe, the fastest human-made object ever, at its peak velocity of 430,000 miles per hour, dives close to the solar surface regularly. The inner solar system is within our technological reach. Step outward again. Light from the Sun takes about 5.5 hours to reach Pluto. The New Horizons spacecraft, travelling at roughly 36,000 miles per hour, took 9.5 years to make that journey. Pluto represents the outer boundary of what humanity has explored with dedicated flyby missions. We have reached the edge of our solar neighbourhood. Now here is the jump that breaks everything. The nearest star system, Alpha Centauri, sits 4.25 light-years away. That is roughly 25 trillion miles. Compared to the distance from the Sun to Pluto, which is about 3.5 billion miles, the jump to Alpha Centauri does not merely add more distance. It multiplies the distance by a factor so large that the entire solar system, everything humanity has ever visited or studied up close, shrinks to a rounding error. The gulf between the outermost planet and the nearest star is not a gap you cross by going a bit farther. It is a gap that belongs to an entirely different category of distance, one that makes the solar system look like a puddle next to an ocean. That single jump from the edge of our solar system to the closest neighbouring star is already beyond anything human engineering has attempted or seriously planned for. At Voyager One's speed of 38,000 miles per hour, The trip to Alpha Centauri would take approximately 75,000 years, and Alpha Centauri is the closest star. It is the nearest front porch. It is the house next door. Crossing the Milky Way is not reaching the house next door. Crossing the Milky Way is reaching a point roughly 23,500 times farther away than Alpha Centauri. If the jump from Pluto to Alpha Centauri multiplied the distance by 7,000, the jump from Alpha Centauri to the far edge of the galaxy multiplies it again by more than 23,000. You are stacking multiplication on top of multiplication, each factor so large that the previous distance becomes a rounding error. This is why the galaxy does not work like a map. A map implies traversability. It implies that the space between 2 points is something you can move through in a reasonable period of time, given sufficient speed or technology. The Milky Way is not that kind of space. The distances within it are so large that they transform the concept of travel from a practical question into something closer to a thought experiment. You can talk about crossing the galaxy, you can calculate the time it would take, but the numbers that come out of those calculations are so far beyond any meaningful human reference frame that the journey stops being a journey and starts being an abstraction. And yet the numbers are real. The galaxy is real. The distances are real. They exist whether we can comprehend them or not. 100,000 light-years of stars, gas, dust, radiation, gravity, and emptiness, stretching from one edge of the disk to the other, every mile of it physical, every mile of it measurable, every mile of it waiting to be crossed by anything brave or foolish enough to try. But how long would that crossing actually take? That depends entirely on how fast you go. And what comes next reveals something deeply unsettling about speed, distance, and the geometry of the galaxy we call home. Because the Milky Way does not merely punish slow travelers, it punishes fast ones too. It punishes every speed humans have ever achieved or even imagined achieving. And it does so with a kind of mathematical brutality that makes the problem feel less like an engineering challenge and more like a fundamental law of cosmic architecture, designed specifically to keep us exactly where we are. Those numbers sit in your mind right now as abstractions. 100,000 light-years, 588 quadrillion miles, 23,500 times the distance to Alpha Centauri. You heard them. You may have even tried to process them, but you did not feel them. Your brain acknowledged the figures the way it acknowledges the national debt or the number of grains of sand on a beach. It filed them under incomprehensibly large and moved on, because that is what human brains do with numbers that exceed lived experience. They round them all down to the same emotional category, big. But big is not good enough here. The distance across the Milky Way is not just big. It is big in a way that is qualitatively different from every other distance you have ever encountered. And the only way to force your intuition to register that difference is to build a ladder of concrete comparisons, rung by rung, starting from things you can actually picture, and then watch as the ladder snaps under the weight of galactic reality. Let us begin with something you can hold in your hand. Take a standard 12-inch classroom globe. On that globe, the distance from New York to London spans roughly 3 inches. The highest mountain on Earth, Everest, would be a bump so tiny you could not feel it with your fingertip. The deepest ocean trench would be an equally invisible scratch. The entire atmosphere, every molecule of air you have ever breathed, would form a film thinner than a coat of varnish. This is your world reduced to something you can spin on a desk. Now, on that same scale, where would the moon be? About 30 feet away, roughly the length of a school bus. You could walk there in 10 seconds. That is the Earth-Moon distance, the farthest any human being has ever physically travelled, reduced to a casual stroll across a classroom. The moon feels close on a globe. It feels achievable, and it was achievable. We went there 6 times. Now, where would the sun be on this scale? Over 2 miles away, a solid 40-minute walk. And the sun itself, at this scale, would be a glowing sphere roughly 100 feet across, about the length of a full-grown blue whale, sitting in a parking lot several neighborhoods from your classroom. The inner solar system, Mercury through Mars, would all fit within that 2-mile radius. Still walkable, still human, still something your body understands. But here is where the first crack opens. Where is Pluto on this scale? Pluto orbits at an average distance of about 3.7 billion miles from the Sun. On our 12-inch globe scale, that places Pluto roughly 88 miles away. Not 88 feet, 88 miles. You have gone from a 40-minute walk to the Sun to roughly the driving distance from New York City to Philadelphia. The solar system, which felt so compact at its inner edge, has suddenly stretched to the size of a small state. And New Horizons, the spacecraft that actually made this journey, needed 9.5 years to cover that distance. That 88-mile hike to Pluto represents the absolute frontier of human exploration. No spacecraft has been sent to a specific destination beyond Pluto. Voyager 1 and 2 have travelled farther, but they were not aimed at any target past the outer planets. They are simply coasting, drifting outward through interstellar space, with no destination and no way to stop. The 88-mile mark on our scale model is the edge of everything humanity has deliberately reached out and touched. Beyond that point, we have only drifters and silence. Now comes the rung that shatters the ladder. Where is Alpha Centauri, the nearest star system, on this scale? Remember, on our 12-inch globe, the Sun is just over 2 miles away and Pluto is 88 miles out. Alpha Centauri, at 4.25 light-years distant, would sit approximately 600,000 miles from your classroom. That is more than twice the real distance from the Earth to the Moon. To visit the nearest star on your scale model, you would need to travel a distance equivalent to 2.5 real trips to the actual Moon. You just went from an 88-mile drive to a 600,000-mile odyssey, and you have not even left the Sun's closest stellar neighborhood. The nearest front porch in the galaxy requires a journey that, even on a shrunken model, dwarfs the greatest voyage humanity has ever accomplished. Sit with that comparison for a moment, because it is the single most important ratio in this entire story. The jump from the edge of the solar system to the nearest star is not a step, it is a chasm. On the scale model, Pluto is 88 miles away. Alpha Centauri is 600,000 miles away. That is a multiplication factor of nearly 7,000. Everything humanity has ever explored, every moon landing, every Mars rover, every Pluto flyby, occupies a zone so tiny compared to the interstellar gulf that it barely registers. If the solar system were a single footstep, the gap to Alpha Centauri would be a 3-mile walk. We have taken the step. We have not even begun the walk, and now we reach the rung where the ladder does not just crack, it disintegrates entirely, because Alpha Centauri is not the destination. Alpha Centauri is the very first star beyond our own, the nearest neighbour in a galaxy containing hundreds of billions of stars spread across 100,000 light-years. On our 12-inch globe scale, we established that Alpha Centauri sits 600,000 miles away. The far edge of the Milky Way, the point you would need to reach to complete the crossing, sits approximately 14 billion miles away on this same scale. Let that register. On a model where the Earth is 12 inches wide and you can hold it in your lap, the opposite edge of the galaxy is 14 billion miles from your classroom. That is nearly 4 times the real-world distance from the Sun to Pluto. Your scale model of the galaxy would stretch from the real Earth past the real orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto, and keep going deep into interstellar space. This is the comparison that breaks human intuition permanently. On a model where the entire Earth shrinks to the size of a globe you can carry under your arm, the galaxy remains so vast that it would engulf most of the inner solar system. You cannot shrink the galaxy down to human scale. You can shrink mountains, you can shrink oceans, you can shrink the solar system to something that fits inside a small town. But the Milky Way resists compression. No matter how tiny you make the Earth, the galaxy stays enormous. It is too large to model at any scale that a human being can physically interact with. The ratio between human accessible distances and galactic distances is simply too extreme. This is not a failure of imagination. It is a mathematical wall. The distances involved span too many orders of magnitude for any single analogy to bridge them. When scientists talk about the Milky Way being 100,000 light-years across, they are describing something that exceeds human spatial intuition by roughly 16 orders of magnitude, compared to the distances we navigate in daily life. For context, the difference between a single grain of sand and the entire diameter of Earth is only 10 orders of magnitude. The galaxy exceeds even that enormous ratio by another factor of 1,000,000. The gap between your commute to work and a trip across the galaxy occupies the same mathematical territory as the gap between a virus and a mountain range. Your brain is not equipped to hold both of those realities simultaneously. Nobody's brain is. The limitation is not intellectual laziness, it is architecture. Human spatial reasoning evolved to track predators across a savanna, to estimate the distance to a water source, and to navigate a few dozen miles of terrain on foot. It did not evolve to process 588 quadrillion miles. Nothing in evolutionary history required that capacity, so it does not exist. This is why analogies matter here more than raw numbers. Numbers fail at this scale, they become noise. But analogies that walk you through the jumps, rung by rung, and force you to notice the moment when each previous step becomes invisible, those can at least approximate the feeling of galactic distance even if they cannot truly replicate it. And the most devastating analogy of all requires no globe, no football field, no walk around the Earth. It requires only a trip to the beach. Pick up a single grain of sand, hold it between your thumb and forefinger. This grain, roughly 0.5 millimeter across, represents the entire solar system. Everything humanity has ever known. Every planet, every moon, every asteroid, every comet, every spacecraft we have launched, every photon of sunlight that has ever warmed your skin, all of it, compressed into a single grain of sand. Now set that grain down on the beach and look around. The Milky Way, at this scale, is the entire beach, not a small beach. A beach stretching dozens of miles in each direction. The sand beneath your feet, the dunes behind you, the coastline extending to the horizon. Every grain on that beach represents a volume of space comparable to our solar system, and there are hundreds of billions of grains. Your grain, the one containing everything you have ever experienced, sits somewhere along one of the outer curves of the shoreline, unremarkable, indistinguishable from its neighbours, surrounded by an unimaginable number of other grains that you will never visit, never see up close, never even confirm contain what you think they contain. Crossing the Milky Way means crossing that entire beach. From your grain of sand to the most distant grain on the opposite shore, miles away, passing over billions of other grains in between. And you are not walking, you are crawling. You are crawling at a pace so slow relative to the beach that you would need millions of years to cover a single stretch of wet sand. That is the scale, that is the reality. That is what the diagram on the poster does not show you. But even the beach analogy, powerful as it is, understates the emptiness of the galaxy. Beaches are packed tight, grain touches grain. The Milky Way is nothing like that. The space between stars is overwhelmingly, oppressively empty. If you placed the sun at the centre of a room the size of a basketball court and shrank it down to the size of a peppercorn, a tiny speck sitting at half court, the nearest star would be another peppercorn sitting in a different city, not a different neighbourhood, a different city, roughly 36 miles away. Everything between those two peppercorns would be void. Blackness. Vacuum. A few stray atoms of hydrogen per cubic centimetre, which is a density so low it qualifies as a better vacuum than anything ever produced in a laboratory on Earth. The interstellar medium is not merely empty by human standards, it is empty by the standards of the best vacuum chambers we can build. And this is typical. This is what most of the galaxy consists of. stars separated by light years of functionally perfect nothingness. But calling it empty does not capture the experience. Empty implies an absence, a blank space waiting to be filled. The interstellar medium is not waiting for anything. It is a positive, hostile, aggressively barren environment with physical characteristics that would destroy any intuitive sense of location, progress, or direction that a human traveler might cling to. The temperature of interstellar space averages roughly 3 degrees above absolute zero, about minus 454 degrees Fahrenheit. That is colder than any natural surface in our solar system, colder than the night side of Pluto, colder than the shadowed craters at the lunar poles. The cosmic microwave background radiation, the afterglow of the Big Bang itself, bathes the entire universe in a faint thermal whisper at 2.7 Kelvin, and in most regions of interstellar space, that whisper is the dominant source of warmth. There is so little matter between the stars that temperature almost ceases to be a meaningful concept. Individual atoms may carry kinetic energy equivalent to thousands of degrees, but they are so sparse that they transfer essentially no heat to anything they touch. A human body exposed to interstellar space would not freeze the way it freezes on a cold night on Earth. It would radiate its thermal energy outward into the void, slowly cooling toward equilibrium with the background radiation, losing heat not because something cold is touching it, but because nothing is touching it at all. The emptiness itself is the cold. The density of this medium is almost impossible to convey in human terms. In the air you are breathing right now, there are roughly 25 quintillion molecules per cubic centimeter. That is a 2 and a 5 followed by 19 zeros. In a typical region of interstellar space between the spiral arms, the density drops to approximately 1 atom per cubic centimeter. Not one molecule, one atom. Usually hydrogen, sometimes helium, occasionally a stray particle of dust smaller than a wavelength of visible light. The ratio between the density of the air in your lungs and the density of interstellar space is comparable to the ratio between the mass of the Earth and the mass of a single grain of table salt. You would need to sweep up the atoms scattered across roughly 27 million cubic kilometers of interstellar medium, a volume comparable to all the glacial ice on the surface of the Earth, just to gather enough matter for a single human breath. The void between stars is not just empty compared to Earth, it is empty compared to emptiness. Laboratory vacuum chambers on Earth, the most sophisticated ones built for semiconductor fabrication and particle physics experiments, achieve pressures of roughly 100 particles per cubic centimeter. The interstellar medium is 100 times emptier than the best artificial vacuum humanity has ever produced. What this means for a traveler is a condition that no human being has ever remotely experienced. There would be no landmarks, no visible features in any direction for years or decades at a time. If your ship were somehow silent, with no internal hum of machinery, no vibration of engines, the external environment would be as close to absolute silence and absolute darkness as the universe can produce. The nearest star behind you would have long since faded to a point indistinguishable from the background starfield. The nearest star ahead of you would not yet have grown noticeably brighter. You would drift in a featureless black void, surrounded by a panorama of stars that change so slowly over decades and centuries that no human eye could detect the movement. There would be no sense of motion, no wind, no resistance. No evidence that you were going anywhere at all, except the steadily climbing number on a navigation readout ticking off miles in the trillions. Interstellar dust would present the only tangible physical feature, and tangible is a generous word. Dust grains in interstellar space are measured in fractions of a micrometer, smaller than the wavelength of visible light, smaller than bacteria, smaller than anything you can see or feel. But they are not harmless. At any significant fraction of the speed of light, a collision with a dust grain delivers energy far out of proportion to its mass. A grain weighing a millionth of a gram, striking a spacecraft at 10% light speed, would release kinetic energy comparable to a hand grenade. At 50% light speed, the the same grain hits with the energy of several kilograms of high explosive. At 99% light speed, a dust grain carries the energy of more than 100 kilograms of TNT. The void is not just empty, it is empty and armed. The faster you cross it, the more dangerous its near-nothingness becomes. This is the texture of galactic distance. It is not merely a large number printed in a textbook. It is trillions upon trillions of miles of frigid, silent, radiation-bathed vacuum, where matter is so scarce it barely qualifies as existing, where temperatures hover just above the theoretical basement of thermodynamics, and where the only physical features you encounter are particles so small they are invisible and so fast-moving relative to your ship that they can punch through metal. This is what fills the spaces between the stars. This is what you would need to endure, mile after mile, year after year, century after century, for timescales longer than civilizations last. The galaxy is not just wide, it is wide and merciless. Every mile of the crossing is a mile of this. This emptiness is crucial to understanding galactic travel times. It is not just that the galaxy is wide, it is that the galaxy is wide and almost entirely vacant. There are no waypoints, no refueling stations, no gravitational assists from conveniently placed objects. Once you leave the immediate gravitational neighborhood of one star, you enter a desert that stretches for trillions of miles before the next star's gravity becomes relevant. The journey across the galaxy is not a highway dotted with rest stops. It is an ocean crossing in a universe where islands are separated by distances that would take centuries to traverse, even at speeds humanity has never achieved. Consider what Voyager One has accomplished. It launched in 1977. It has been traveling through space for nearly 48 years. It is currently more than 15 billion miles from Earth, moving at approximately 38,000 miles per hour. It has crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space. By any human standard, Voyager One has traveled an extraordinary distance. It is the farthest human-made object in existence, and in galactic terms it has gone essentially nowhere. 15 billion miles is approximately 0.0026 light-years. The galaxy is 100,000 light-years across. Voyager 1 has covered roughly 1/40,000,000th of the distance needed to cross the Milky Way. If the galactic crossing were a marathon, 26.2 miles, Voyager 1 has travelled less than 1/16th of an inch after nearly half a century of continuous flight. You would need a magnifying glass to find its progress on a marathon course map. You would need a microscope to measure it. This is not a reflection of Voyager's inadequacy. Voyager 1 is a triumph of human engineering. It was designed to explore the outer planets, and it did so brilliantly, returning some of the most iconic images in the history of science. But its journey reveals with merciless clarity the mismatch between human capability and galactic geometry. We built the fastest sustained interstellar traveller in human history, and after nearly 5 decades of flight, its contribution to crossing the galaxy would be invisible on any map drawn at galactic scale. There is a tendency, when confronted with these comparisons, to retreat into optimism. Surely future technology will close the gap. Surely faster engines, better propulsion, more advanced spacecraft will make interstellar distances manageable. And that instinct is not entirely wrong. Humanity will almost certainly build faster spacecraft. Ion drives, solar sails, nuclear pulse propulsion, laser-driven light sails, these are all concepts under active development or serious theoretical study. Some of them could plausibly accelerate a small probe to a few percent of the speed of light. Projects like Breakthrough Starshot have proposed sending gram-scale probes to Alpha Centauri at 20% light speed, arriving in roughly 20 years. That would be an extraordinary achievement, a genuine leap beyond anything we have done before. But here is the critical distinction that optimism tends to blur. Reaching Alpha Centauri and crossing the galaxy are not the same problems scaled up. They are different problems separated by a factor of more than 23,000. If Breakthrough Starshot succeeds and sends a probe to Alpha Centauri at 20% the speed of light, arriving in roughly 20 years, the same technology aimed at the far edge of the Milky Way would require approximately 500,000 years to complete the journey. 500,000 years. At 20% the speed of light, a speed that no macroscopic spacecraft has ever approached, and that would require energy investments beyond anything currently possible. Even that extraordinary technological leap, which has not yet been achieved, would produce a travel time so long that the entirety of human civilization, from the first Sumerian city-states to the present day, represents barely 1% of the journey duration. This is the trap that galactic distance sets for human ambition. Every improvement in speed that feels revolutionary, every breakthrough that seems to bring the stars within reach, gets crushed by the sheer multiplication factor that separates nearby stars from the galactic far side. You can double your speed. You can multiply it by 10. You can multiply it by 100. And the galaxy absorbs each improvement without flinching, returning travel times that remain measured in hundreds of thousands or millions of years. The distance is not just large. It is large in a way that resists technological rescue. It is large enough that even technologies we have not yet invented, technologies that might seem like magic to us today, would still produce journey times longer than the lifespan of most species that have ever existed on Earth. To appreciate just how stubbornly the galaxy resists compression, consider the following thought experiment. Imagine you could magically accelerate a spacecraft to the speed of the fastest human-made object ever, the Parker Solar Probe, at its peak velocity of 430,000 miles per hour. That speed, achieved briefly during close solar passes in late 2024, is roughly 0.064%, the speed of light. It is 11 times faster than Voyager One. At that velocity, you could fly from New York to Los Angeles in about 20 seconds. You could reach the moon in roughly 33 minutes. You could arrive at Mars in just a few days at closest approach. These are dizzying speeds by any terrestrial standard. Now point that spacecraft at the far edge of the galaxy. At 430,000 miles per hour sustained, the crossing would take approximately 156 million years. 156 million years ago, the dinosaurs had not yet gone extinct. The Atlantic Ocean was narrower than it is today. India was an island drifting northward toward a collision with Asia that would eventually raise the Himalayas. The Earth itself was fundamentally different. Not just culturally or technologically different in the way it has changed during human history, but geologically, biologically, climatically different at a planetary level. The continents had different shapes. The atmosphere had different composition. The dominant life forms bore no resemblance to modern animals. That is the timescale. The fastest sprint humanity has ever achieved, applied to the width of the galaxy, produces a journey longer than the age of flowering plants. And this is the moment where the ladder truly breaks. Because you have now exhausted every rung. You started with the Earth and Moon, a distance humanity has actually covered. You climb to the Sun, to Mars, to Pluto, distances our probes have reached. You leap to Alpha Centauri, a distance no probe has crossed but that near-future technology might theoretically bridge within decades. And now you are staring at the far edge of the galaxy, 100,000 light-years away, and there are no more rungs. There is no technology in development, no propulsion system under study, no theoretical framework in mainstream physics that offers a plausible path to crossing the galaxy within any time frame that a human civilization could survive, let alone a human life. The ladder does not just fail to reach the top, it reveals that there is no top. The galaxy is not the final rung of a very tall ladder. It is the point where the concept of a ladder stops making sense. Ladders are for distances that can be bridged incrementally. The Milky Way is a distance that defeats incrementalism. Each step you take, no matter how large, leaves you facing a remaining distance so enormous that your step is undetectable. You cannot inch your way across a galaxy. The math does not allow it. The timescales do not permit it. The distance absorbs every effort and returns a number that makes the effort feel meaningless. And yet the galaxy is right there. You can see it tonight. Step outside on a clear night, far from city lights, and that luminous band of stars stretching across the sky. That is it. That is the structure we have been discussing. 100,000 light-years of stars and gas and dust and emptiness spread across the sky so close it feels like you could reach up and run your fingers through it. The Milky Way does not look 100,000 light-years wide when you see it with your eyes. It looks intimate. It looks close. It looks like home. And that is perhaps the cruelest trick of galactic distance. The galaxy presents itself to your senses as a neighborhood, a familiar glow above your head, a comforting presence on a dark night. It hides its true nature behind the limitations of human perception. You see the glow, but not the gulf. You see the light, but not the void between the sources. The Milky Way shows you its beauty and conceals its brutality. What comes next will take the comparison further than comfort allows. We are going to ask a simple question. What if we actually tried? What if we launched a spacecraft today, or 100 years from now, or 1,000 years from now? At every speed, from the merely ambitious to the physically impossible, how long would each attempt take? And the answers will reveal something that goes beyond impressive, or challenging, or even daunting. They will reveal that the galaxy does not merely resist crossing, it renders the concept almost meaningless. We built the ladder and watched it collapse. You saw the distances stack up from the Moon to Mars to Pluto to Alpha Centauri to the galactic edge, each rung multiplying the last by factors so large that every previous step shrank to invisibility. But that collapse was a collapse of spatial intuition. You understood that the galaxy is wider than your brain can picture. You understood that no analogy fully captures 588 quadrillion miles. What you may not yet understand is something far more disturbing. The galaxy does not just defeat your sense of distance, it defeats speed itself. Every speed. All of them. From the slowest crawl humanity has achieved to the fastest velocity permitted by the laws of physics. The Milky Way takes each one, processes it through simple division, and returns a travel time so long it makes the effort feel like a cruel joke. This is about that joke. It is about what happens when you actually try to cross the galaxy, not with optimism, not with speculation, but with mathematics. And it is about the moment you realize that the problem is not a lack of engineering. The problem is the universe itself. Let us start where humanity actually stands. Our fastest interstellar traveler, Voyager One, moves at approximately 38,000 miles per hour. That is roughly 17 kilometers per second. In everyday terms, that speed would carry you from Los Angeles to New York in about 4 minutes. It would get you to the Moon in roughly 6 hours. It is a speed that would be nearly incomprehensible to anyone born before the 20th century. And it is laughably, tragically, almost insultingly slow compared to the Milky Way. At Voyager 1's speed, crossing the galaxy would require approximately 1.77 billion years. Say that number out loud. 1.77 billion years. Not million, billion. To give that duration a concrete anchor, consider what Earth looked like 1.77 billion years ago. There were no animals. There were no plants. There were no fungi. The most complex life forms on the entire planet were single-celled organisms, some of which had only recently figured out how to bundle together into rudimentary colonies. Multicellular life as we know it did not exist. The atmosphere contained only a fraction of the free oxygen it holds today. The continents were barren slabs of rock baking under a sun that was dimmer than it is today. If you had stood on the shore of that ancient Earth and launched a spacecraft at Voyager 1's speed toward the far edge of the galaxy, and if that spacecraft somehow survived every hazard of interstellar space for nearly 2 billion years, it would be arriving right about now. The entire history of complex life on Earth, every organism more sophisticated than a blob of cells, fits inside the travel time. Every fish, every dinosaur, every mammal, every primate, Every human being who has ever drawn breath occupies a sliver of the timeline, so thin it would not show up on a graph. That result should stop you cold. But the natural human response is to think about going faster. Fine, Voyager is slow. What about something quicker? And this is where the trap reveals its teeth, because the galaxy punishes faster speeds with the same impersonal brutality. You can climb the speed ladder as high as you want. The galaxy adjusts the travel time, hands it back to you, and the number is still devastating. Take the Parker Solar Probe, the fastest human-made object ever constructed. During its closest approaches to the Sun in 2024 and 2025, it reached a peak velocity of approximately 430,000 miles per hour. That is 0.064% the speed of light. It is roughly 11 times faster than Voyager One. At that blistering pace, you could fly from Earth to Mars in a matter of days rather than months. You could reach Jupiter in a few weeks. It feels fast because it is fast, at least by the standards of anything humans have ever built. Crossing the Milky Way at 430,000 miles per hour would take approximately 156 million years. You have multiplied your speed by 11, and you have shaved off roughly 91% of the travel time. That sounds like progress until you examine what 156 million years actually means. That is more than twice the span since the asteroid that killed the non-avian dinosaurs struck the Yucatan Peninsula. It is older than the Rocky Mountains. It is older than the modern Atlantic Ocean at its current width. The continents of Earth would rearrange themselves multiple times during the journey. Species would arise, dominate the planet, and go extinct in cycles that repeat dozens of times before the spacecraft reach the halfway mark. The fastest object humanity has ever created reduces the galactic crossing from 1.75 billion years to 156 million years, and both of those numbers land so far outside human experience that the improvement is emotionally meaningless. You have traded one incomprehensible number for a slightly smaller incomprehensible number, so let us push harder. Forget about current technology. Forget about rockets and gravity assists and solar sails. Imagine a spacecraft traveling at 1% the speed of light. That is roughly 6.7 million miles per hour. No spacecraft, no bullet, no explosion, no particle accelerator product on Earth moves at this speed in any sustained way. Achieving 1% light speed with a macroscopic payload would require energy budgets so far beyond current capability that the engineering challenges alone could occupy physicists for centuries. But let us assume we solve those challenges. Let us assume we build the engine, generate the fuel, and accelerate a ship to 1% the speed of light. How long does the crossing take? 10 million years. At 1% of the absolute cosmic speed limit, the journey across our own galaxy requires 10 million years. The human species, Homo sapiens, has existed for roughly 300,000 years. 10 million years is more than 33 times the entire duration of our species. Every stone tool, every cave painting, every empire, every war, every scientific discovery, every love story and funeral and sunrise that any human being has ever experienced fits inside less than 3% of the travel time. At 1% light speed, you would cross the Milky Way and arrive at the other side to find that the species that launched you had, in all probability, either evolved into something unrecognizable or ceased to exist entirely. The Earth that sent you off would be a different planet. Not metaphorically different. Geologically, climatically, biologically different. Coastlines shifted, ice ages come and gone multiple times, entire branches of the evolutionary tree grown, flourished, and vanished. The journey would outlast not just your civilization but your entire biological lineage. Perhaps 1% is too modest. Let us try 10% the speed of light, 67 million miles per hour. This is the realm of serious speculative propulsion. Nuclear pulse drives, antimatter engines, concepts that live on the boundary between ambitious physics and outright science fiction. 10% light speed is a velocity at which relativistic effects begin to become noticeable, though they are still modest at this fraction. The kinetic energy of a ship-mass object at 10% light speed would be staggering, equivalent to multiple nuclear arsenals packed into the motion of a single vessel. But assume it is done. Assume the impossible engine is built, the impossible fuel is loaded, and the ship is hurled across the galactic disk at 10% the speed of light. Before we look at that travel time, it is worth pausing to understand just how staggering the energy requirement actually is, because the numbers reveal a barrier almost as impassable as the distance itself. The kinetic energy of a moving object scales with the square of its velocity at everyday speeds and climbs even more steeply as you approach light speed, due to relativistic mass increase. At low speeds, doubling your velocity quadruples the energy needed. At high fractions of light speed, the relationship becomes far more punishing. Let us make it concrete. Consider a spacecraft with a mass of 10,000 metric tons. That is roughly 25 times the mass of the International Space Station, still modest for any vessel expected to sustain a crew across interstellar distances, but useful as a benchmark. Accelerating 1,000 metric tons to 1% of the speed of light requires approximately 4.5 times 10 to the 19th joules of energy. For comparison, the total energy consumption of the entire human civilization in a year is roughly 5.8 times 10 to the 20th joules. So accelerating a single 10,000-ton spacecraft to 1% light speed would consume roughly 8% of the world's total annual energy output. That is the energy produced by every power plant, every engine, every furnace, every battery on the planet over an entire year, and you would need to focus nearly a tenth of it into a single spacecraft. And 1% light speed, as we have seen, still produces a crossing time of 10 million years. The speed is not fast enough, and the energy cost is already civilizational in scale. Now raise the speed to 10% light speed. Energy scales roughly with the square of velocity at these subrelativistic speeds, so you need approximately 100 times more energy. That is roughly 4.5 times 10 to the 21st joules. This exceeds the total annual energy output of human civilization by a factor of almost 8. You would need to harness approximately 8 years of total global energy production and channel it entirely into accelerating a single ship-mass object. No heating, no lighting, no transportation, no industry. Every watt produced on Earth for 8 straight years poured into one spacecraft. And even if you could do it, the trip still takes 1 million years. At 50% light speed, the relativistic effects become significant and the energy climbs dramatically. The Lorentz factor at half-light speed is approximately 1.15, which increases the effective mass of the spacecraft by 15%. The kinetic energy required reaches approximately 1.4 times 10 to the 23rd joules. That is roughly 240 years of total global energy production. The entirety of human industrial civilization since the steam engine, every kilowatt hour ever generated by coal, oil, nuclear, solar, wind, and hydro combined, would not be enough. You would need to multiply that total by roughly 9. At 99% light speed, the Lorentz factor climbs to approximately 7.1, meaning the relativistic mass of the spacecraft has increased 7-fold. The energy required approaches 5.5 times 10 to the 24th joules. This is roughly 9,500 years of total human energy production. But even this incomprehensible figure understates the problem, because we have been talking about acceleration only. We have not discussed deceleration. A spacecraft arriving at its destination at 99% light speed needs to slow down, or it will flash past in a fraction of a second after a journey of 100 millennia. Decelerating from 99% light speed requires the same energy as accelerating to it. The total energy budget for a round-trip speed profile, accelerate and decelerate, doubles to roughly 19,000 years of global energy output for a single ship. And here is the factor that makes all of this truly impossible. These calculations assume 100% efficiency. Every joule of energy produced goes directly into accelerating the spacecraft with zero waste, zero heat loss, zero inefficiency of any kind. No real propulsion system achieves anything close to this. Chemical rockets operate at efficiencies measured in fractions of a percent when you account for the mass of fuel they must carry. Even theoretical antimatter drives, which convert mass directly into energy via matter-antimatter annihilation, face enormous practical losses. The real energy requirements for any physically plausible propulsion system would be orders of magnitude higher than the theoretical minimums described above. The energy barrier does not merely complement the distance barrier, it reinforces it from a completely different direction. Even if the travel times were acceptable, even if you were willing to spend 1,000,000 years crossing the galaxy, you would still face the problem of generating and focusing more energy than your entire civilization produces in centuries, possibly millennia, into a single vehicle. The galaxy demands not just time you cannot spare, but energy you cannot produce. It attacks the problem from both flanks simultaneously, and neither flank shows any sign of yielding. The crossing takes 1,000,000 years. 1,000,000 years. A number that finally begins to feel approachable, perhaps, compared to the billions and hundreds of millions that preceded it. But do not let the relative modesty of 1,000,000 years fool you into thinking it is manageable. 1,000,000 years ago, Homo sapiens did not exist. Our ancestors were Homo erectus, a species that had mastered fire and basic stone tools but had not developed complex language, symbolic art, agriculture, or any of the higher cognitive capacities that define modern humanity. The entire arc of human cultural evolution, from the first controlled fires to the International Space Station, occupies less than a third of 1,000,000 years. The species itself has changed physically and cognitively over far shorter spans, meaning the beings who arrive would bear little resemblance to the beings who departed. The oldest known human structures are roughly 12,000 years old. The oldest continuously spoken language lineage is maybe 10,000 years old, and even that has changed beyond recognition from its original form. 1,000,000 years is not a long time on an astronomical scale, but it is an eternity on a human one. It dwarfs every social structure, every political system, every cultural tradition humanity has ever produced, by factors of 100. This is the point where the concept of a generation ship usually enters the conversation. If the journey takes 1,000,000 years, perhaps you do not send individuals. Perhaps you send a self-sustaining colony, a ship large enough to house thousands of people who live, reproduce, and die aboard the vessel, while their descendants continue the journey. Generation after generation, the ship crawls toward its destination, a civilization unto itself hurtling through interstellar space. The idea is romantic. It is also, at galactic scales, absurd. Consider the engineering. A generation ship capable of sustaining a human population for 1,000,000 years would need to maintain its hull integrity, its life support systems, its food production, its social structures, and its navigational accuracy across roughly 40,000 human generations. 40,000 successive generations of human beings, each born, raised, and buried inside the same vessel, each inheriting the mission from the previous generation and passing it to the next. For context, the entirety of recorded human history spans roughly 250 generations. The total span from the first anatomically modern humans to the present is roughly 12,000 generations. A 1,000,000-year generation ship would need to sustain coherent purpose and functional systems for more than 3 times the number of generations that separate us from the emergence of our species. No material we know of lasts that long without degradation. No sealed ecosystem has maintained balance for more than a few years in laboratory settings. The engineering requirements alone span timescales that mock every structure humanity has ever built. The generation ship is a concept that works beautifully for journeys of a few centuries. At galactic timescales, it becomes a fantasy dressed in engineering language, but the generation ship problem exposes something even deeper than engineering failure. It exposes the certainty that you are not just leaving a place, you are leaving a time, and the time you leave will not wait for you. Consider what Earth looks like after each of the timescales we have discussed. At 10 million years, the duration of a crossing at 1% light speed, the continents will have shifted noticeably. The Atlantic Ocean will be over 100 miles wider. The Mediterranean Sea will have narrowed dramatically, squeezed by the slow northward drift of Africa into Europe. Mountain ranges that do not currently exist will have risen and begun to erode. Rivers will have carved new valleys. Coastlines will bear no resemblance to modern maps. Tens of thousands of species currently alive will have gone extinct, replaced by descendants adapted to environments that do not yet exist. If any trace of human civilization survives, it will be geological, faint chemical signatures in sedimentary rock, a thin stratum of unusual isotopic ratios and microplastics, marking the era when one species briefly reshaped the planet's surface. No building will remain, no road, no city, no dam. Erosion, tectonic recycling, and biological decomposition will have reclaimed everything. The species that launched your ship will be as distant to whatever inhabits the Earth as the first fish are to you. At 1 million years, the timescale of a 10% light-speed crossing, the changes are less dramatic but no less total from a human perspective. Languages will have transformed beyond all recognition. Linguistic studies suggest that languages become mutually unintelligible within roughly 500 to 1,000 years of separation. After 1 million years, the descendants of every language currently spoken on Earth would share no recognizable vocabulary, grammar, or phonetic system with their ancestors. Every word you know will be extinct. Every story, every song, every joke, every prayer will have been forgotten, reinvented, forgotten again, and reinvented in forms you would not recognize as related to the originals. Political and social structures will have cycled through thousands of iterations, the longest-lasting human institutions that have ever existed. Certain religious traditions, certain monarchies, lasted roughly 2,000 to 3,000 years. 1 million years contains 300 to 500 complete cycles of rise, dominance, decline, and collapse of the most durable institutions humanity has ever built. Whatever exists on Earth after 1 million years will be as foreign to you as the culture of Homo erectus is to a modern human. More foreign, because at least Homo erectus was the same genus. After 1 million years of evolution, your descendants may not be. Even at the light speed minimum of 100,000 years, the erasure is nearly complete. 100,000 years ago, anatomically modern humans existed, but behavioral modernity, art, complex language, symbolic thought was only beginning to emerge. The entire arc of human cognitive and cultural development fits inside 100,000 years. If you launched a light-speed ship today and arrived at the far edge of the galaxy, you would step out into a universe where Earth has undergone as much change as separates the first cave paintings from the smartphone in your pocket. Everything you knew, everyone you loved, every institution you served, every nation you belonged to, will be not just gone but archaeologically unrecoverable. You will have arrived somewhere, but you will have come from nowhere, because the place you left will have ceased to exist in every sense that matters to a conscious being. This is the dimension of galactic crossing that pure mathematics obscures. The numbers tell you how long the trip takes. They do not tell you what the trip costs in human terms, and the cost is total. It is the complete severance of every connection to everything you have ever known. It is not a journey you return from, because there is nothing to return to. The galaxy does not just demand your time, it demands your past. It demands the world that sent you. It demands the erasure of your origin as the price of your arrival, and no speed fast enough to be interesting is fast enough to avoid paying that price. So let us abandon realism entirely. Let us go to the absolute limit, the speed of light, 186,000 miles per second, 670 million miles per hour. the fastest anything can move through the fabric of space-time according to every confirmed experiment in physics. Nothing with mass can actually reach light speed. Einstein's special relativity demonstrates that as an object with mass accelerates toward the speed of light, the energy required to continue accelerating increases without bound. Approaching infinity as you approach light speed, you would need infinite energy to push a physical object to the speed of light. It cannot be done. But let us pretend. Let us wave away physics and ask the simplest possible question. If you could travel at the speed of light itself, how long would it take to cross the Milky Way? 100,000 years. That is not a calculation, that is a definition. The galaxy is 100,000 light-years wide. Light takes 100,000 years to cross it. That is what the unit means. And 100,000 years is the most optimistic possible answer the universe will ever give to this question, because nothing can go faster. Light speed is not a speed limit in the way that a highway speed limit is a speed limit. It is not an arbitrary rule imposed by an authority that could choose a different number. It is woven into the geometry of space-time itself. The speed of light is the rate at which causality propagates through the universe. Exceeding it does not just require better technology. It requires a different universe operating under different physical laws. In this universe, with these laws, 100,000 years is the basement. It is the minimum possible crossing time. And it is a duration that stretches roughly 10 to 20 times longer than the entire history of human civilization. Now, there is a subtlety here that demands attention, because it is often misunderstood and sometimes offered as a kind of escape hatch from the problem of galactic distance. Special relativity contains a phenomenon called time dilation. When an object moves at a significant fraction of the speed of light relative to another observer, time passes more slowly for the moving object than for the stationary one. This is not a thought experiment or a theoretical curiosity. It is confirmed physics, measured in particle accelerators and observed in the behavior of cosmic rays. Time dilation means that a traveler moving at very high speed would experience less elapsed time than an observer watching from Earth. At modest fractions of light speed, the effect is negligible. At 10% light speed, time on the ship would pass roughly 0.5% more slowly than time on Earth, barely noticeable. But at extreme fractions, the dilation becomes dramatic. At 90% light speed, time on the ship passes about 2.3 times slower than on Earth. At 99% light speed, the factor jumps to roughly 7. At 99.99%, the factor reaches about 70. And at 99.9999%, the dilation factor reaches roughly 700. This means that, in principle, a traveller moving at 99.99% of light speed could cross the galaxy in what feels to them like roughly 1,400 years of onboard time, while 100,000 years pass in the outside universe. Push the speed even closer to light speed, piling nines onto the decimal, and you can compress the subjective experience further. At 99.9999%, the traveller might experience roughly a century and a half while the galaxy ages 100 millennia around them. This sounds like a solution. It is not. Time dilation is real, but it does not shrink the galaxy. It shrinks the experience of the traveller. The universe outside the ship still ages at full speed. 100,000 years still pass for everyone and everything not aboard the vessel. The Earth the travellers left behind undergoes 100,000 years of geological change, biological evolution, and civilizational transformation. By the time the ship arrives at the far edge of the galaxy, the civilization that launched it has been gone for thousands of centuries. Any message sent back would take another 100,000 years to arrive. There is no one to receive it. Time dilation allows you to survive the crossing in a personal sense, but it does so by detaching you from everything and everyone you have ever known by a temporal gulf so vast that the word return loses its meaning. You are not crossing the galaxy and coming home. You are crossing the galaxy and arriving in a future so distant that it constitutes a different world. There is also the energy problem, which time dilation does nothing to solve. Accelerating a spacecraft to 99.99% of light speed requires energy inputs that dwarf anything humanity has produced in its entire history. The kinetic energy of even a modest ship at that velocity would exceed the total energy output of the Sun over several days. Sustaining that speed, navigating around interstellar debris at a velocity where a collision with a grain of dust would release energy comparable to a bomb, decelerating at the other end so you do not simply fly past your destination at nearly the speed of light. These are problems so far beyond current engineering that calling them challenges understates the gulf by orders of magnitude. And here is the deepest cut of all. Everything discussed so far assumes travel in a straight line, unimpeded, through empty space. The actual galaxy is not empty. It contains gas clouds, dust lanes, star systems, gravitational fields, radiation zones, and the dense, chaotic environment near the galactic center. Any real crossing would need to navigate these hazards or account for the drag and deflection they impose. The straight-line distance of 100,000 light-years is a theoretical minimum. A practical crossing, if such a thing could ever exist, would be longer. Let us assemble the results into a single unflinching summary. At Voyager One speed, the crossing takes 1.77 billion years. At the Parker Solar Probe's peak speed, 156 million years. At 1% light speed, 10 million years. At 10% light speed, 1 million years. At 50% light speed, 200,000 years. At 90% light speed, roughly 111,000 years. At 99%, approximately 101,000 years. At light speed itself, 100,000 years flat. The progression is revealing. You gain enormous reductions at the lower end of the speed range. Going from Voyager speed to 1% light speed cuts the travel time by a factor of nearly 200. But as you climb into the high fractions of light speed, the returns diminish savagely. Going from 50% to 90% light speed saves you less than 90,000 years. Going from 90% to 99% saves barely 10,000. Going from 99% to 100%, crossing a boundary that physics says cannot actually be crossed, saves you only about 1,000 years. The galaxy gives back less and less for each increase in speed, guarding the final 100,000 years with the stubbornness of a physical law, because that is exactly what it is. The speed of light is the floor. You cannot dig beneath it. 100,000 years is the absolute minimum, and it is a duration that exceeds the entire history of human agriculture, human cities, human writing, human science, and human art combined, multiplied by 10. This is what it means to brace yourself. The Milky Way does not merely resist being crossed at slow speeds, which would be understandable and even expected. It resists being crossed at fast speeds. It resists being crossed at the fastest speed the universe allows. The galaxy is not a container that technology can shrink. It is a geometrical fact built into the structure of space-time. 100,000 light-years is not a challenge to be overcome. It is a feature of reality. As fixed and non-negotiable as the charge of an electron or the mass of a proton, you can resent it. You can admire it. But you cannot change it. The numbers we have walked through are not speculative. They are arithmetic. Distance divided by speed equals time. The distance is confirmed by decades of astronomical observation. The speeds are either measured directly or derived from well-understood physics. The travel times follow inescapably. There is no hidden variable, no secret shortcut, no wormhole conveniently placed at the galactic center that rescues the journey from its mathematical verdict. There is only the galaxy, vast beyond intuition, and the speed of light, fast beyond experience, and the division of the former by the latter, which produces a number that should permanently alter how you think about the place you live. Because you do live here. You live inside this structure. You were born in it, and you will die in it. And every human being who has ever existed or ever will exist will share that fate. The Milky Way is your home in the most literal sense possible, and it is a home you cannot cross, not because you lack the will, not because you lack the imagination, not because you lack some future technology that a smarter species might invent, but because the galaxy is built on a scale where crossing it requires more time than your species has existed, more time than complex life has existed, more time than the journey has any right to demand of a living thing. What that means for humanity's place inside this uncrossable home, what it means for how we think about distance, ambition, and the boundaries of the possible is where this story ends, and where a much harder truth begins. You now hold the numbers. You have seen the ladder built and broken. You have watched speed after speed thrown against the width of the galaxy and returned as a travel time measured in epochs. 100,000 years at light speed, 1 million years at 10%, 10 million years at 1%, 156 million years at the fastest velocity any human-made object has ever achieved, 1.77 billion years at the speed of Voyager One, the farthest thing we have ever sent into the dark. These are not estimates. They are not guesses. They are the results of dividing a confirmed distance by confirmed or hypothetical speeds, and every result lands so far outside the boundaries of human experience that the question this script was built around, how long would it really take to cross the Milky Way, stops being a question about engineering or technology or ambition. It becomes a question about what kind of universe we actually live in. And the answer to that question is one that most people have never been forced to sit with. You live in a galaxy you cannot cross, not because crossing it is hard. Hard implies difficulty that effort can overcome. Climbing Everest is hard. Building a particle accelerator is hard. Landing on the moon was hard. Crossing the Milky Way is not hard. It is structurally excluded from the category of things that effort, ingenuity, or time can accomplish within any framework that connects to human existence. The galaxy is not presenting you with a challenge. It is presenting you with a boundary, as fundamental and impassable as the speed of light itself, because it is the speed of light itself multiplied by a distance so large that even the cosmic speed limit cannot redeem it. This is a strange thing to realize about your own home. We call the Milky Way home. Every astronomy textbook, every documentary, every planetarium show invites you to think of the galaxy as your cosmic address. You live on Earth, in the solar system, in the Orion Arm, in the Milky Way galaxy. The language implies belonging. It implies residence. It implies the kind of relationship a person has with a house or a neighborhood or a city, the kind of place you can explore, learn the shape of, move through. But the relationship between a human being and the Milky Way is nothing like the relationship between a person and a house. It is more like the relationship between a bacterium and the ocean it floats in. The bacterium exists within the ocean. It is surrounded by it on all sides. It is made of materials drawn from it. In some technical sense, the ocean is its home, but the bacterium will never cross the ocean. It will never see more than an infinitesimal fraction of its volume. It will be born, live, and die in one negligibly small region, while the overwhelming majority of its home remains permanently beyond its reach. The ocean does not care about the bacterium. The ocean does not even know the bacterium is there. That is your relationship with the Milky Way. You live in it the way a microbe lives in the Pacific. The galaxy surrounds you. It defines the cosmic structure you inhabit. Its gravity holds your star in orbit. Its heavy elements, forged in ancient supernovae, compose your bones and blood. In every physical sense, you belong to this galaxy. And in every practical sense, the galaxy is closed to you. Not most of it, virtually all of it. Consider the numbers carefully. The solar system, the region humanity has actually explored with spacecraft, extends out to roughly 100 astronomical units. If you include the scattered disk objects beyond Pluto, perhaps 2,000 astronomical units. If you include the inner edge of the hypothesized Oort cloud, 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. 2,000 astronomical units is roughly 3/100th of a light year. The Milky Way is 100,000 light years across. The volume of space that humanity has even remotely explored represents less than 1/1,000,000,000th of 1% of the galaxy's volume. You could replicate the explored solar system trillions of times and still not fill a single spiral arm. Everything humanity has seen, touched, photographed, sampled, or studied with a physical instrument exists within a cocoon of space, so tiny compared to the galaxy that no visual representation can accurately depict both at the same scale. If the Milky Way were the size of the continental United States, the entire volume of space that humanity has explored with spacecraft would fit inside a single basketball. Now extend the boundary outward to include the nearest stars. Alpha Centauri sits 4¼ light years away. Barnard's star is about 6 light years. Wolf, 359, is roughly 8. Sirius, the brightest star in the night sky, lies 8½ light years from Earth. Within 20 light years, there are roughly 130 known star systems. This is the realistic frontier of human ambition for the next few centuries. Projects like Breakthrough Starshot aspire to send tiny probes to Alpha Centauri within a generation. Larger, crewed missions to nearby stars remain firmly in the domain of speculation, but they are at least conceivable within the laws of physics using technologies that could plausibly be developed in the coming centuries. The nearby stellar neighbourhood, a sphere of perhaps 50 light years centred on the Sun, represents the outermost boundary of what humanity might meaningfully explore within the next millennium if everything goes extraordinarily well. 50 light years out of 100,000. That is 1/20th of 1% of the galactic diameter. A sphere 50 light years in radius, encompassing every star system humanity might ever physically visit in the next 1,000 years of optimistic technological development, contains less than 1/1,000,000th of the galaxy's total volume. This is not pessimism. This is geometry. The galaxy is so large that even an aggressive multi-century expansion program that pushes humanity to dozens of nearby star systems would leave 99.9999% of the Milky Way untouched. We would spread across a small cluster of stellar neighbours and call it an interstellar civilization, and the galaxy would not notice. There is a word for this situation that nobody likes to use in the context of space exploration. The word is confinement. Humanity is confined, not by walls, not by a lack of vision, not by any technological barrier that ingenuity can dismantle. Confined by the raw, brute, inarguable width of the galaxy and the fixed speed at which information and matter can move through it, you are free to go anywhere you want within the Milky Way. The galaxy imposes no gatekeepers, no barriers, no permissions. It simply demands that you spend 100,000 years to reach the far side, even if you somehow achieve light speed, and it knows that this price is one no human being, no human society, no human species can afford to pay. The confinement is enforced not by restriction, but by cost. You are free to cross the ocean. You simply cannot survive the swim. This confinement has consequences that ripple outward in every direction. Consider communication. Even if a civilization exists on the far side of the Milky Way right now, broadcasting radio signals in every direction, the signals arriving at Earth tonight left their source 100,000 years ago. They carry news of events that occurred before the last ice age, before the first human city, before the domestication of the first animal. If we detected such a signal and immediately replied, our response would arrive at their location 100,000 years from now, carrying information about a civilization that has, in all likelihood, transformed beyond recognition or ceased to exist entirely in the interim. The round-trip communication time with the far side of the galaxy is 200,000 years. The concept of a conversation, of back-and-forth exchange, of dialogue, becomes meaningless at this timescale. You are not communicating. You are launching messages into a future so distant that the word reply no longer applies. This temporal abyss applies not just to the far side of the galaxy but to most of it. A star system 30,000 light-years away, which is not even on the opposite side but merely on the other side of the galactic center, would require 60,000 years for a round-trip message at light speed. That is longer than the entire span of modern human civilization multiplied many times over. The galaxy is not just too wide to cross. It is too wide to talk across. Every region beyond a few thousand light-years exists in a state of communicative isolation, so profound that the concept of a galactic community, a galaxy-spanning network of civilizations sharing information and culture, is not merely difficult, it is physically precluded by the geometry of space-time. This realization carries a weight that is easy to intellectualize and difficult to feel. We are accustomed to thinking of isolation as something that can be overcome. Throughout human history, every barrier to communication and travel has eventually fallen. Oceans were crossed, continents were connected by telegraph, then telephone, then fiber optic cable. The moon was reached. Mars was photographed up close. The pattern of human progress has been a steady, triumphant expansion of reach, and it has conditioned us to expect that the trend will continue indefinitely. Galactic distance breaks this expectation. It does not bend to technological progress. It does not yield to determination. It sits at the intersection of distance and the speed of light, two quantities that are not subject to engineering, and it produces timescales that no amount of cleverness can compress below a floor of 100,000 years. There is a temptation here to invoke exotic physics. Wormholes, warp drives, Alcubierre metrics, shortcuts through higher dimensional space. These concepts exist in theoretical physics, and they make for thrilling science fiction, but they remain, as of today, entirely speculative. No wormhole has ever been observed. No warp drive has ever been built or tested. The Alcubierre metric, while mathematically valid within general relativity, requires forms of energy, specifically negative energy density, that have never been produced in any quantity and may not be producible at all. Invoking these concepts to solve the problem of galactic distance is like invoking magic to solve the problem of mortality. It is not wrong to hope, it is not wrong to theorize, but it is wrong to treat unverified speculation as a counterargument to confirmed physics. The speed of light is confirmed. The width of the galaxy is confirmed. The resulting travel times are confirmed. Everything else is hope, and hope is fine. Hope is human. But this script is not about hope. It is about reality. And the reality is this. You live inside a structure 100,000 light-years wide. You are located roughly 26,000 light-years from its center. The nearest edge of the disk is tens of thousands of light-years away. The far edge is about 76,000 light-years from your position. Even the center of your own galaxy, the supermassive black hole around which your star has been orbiting for 4.5 billion years, is so far away that light from it takes 26,000 years to reach you. You have never seen the galactic center as it exists now. You have only ever seen it as it existed 26,000 years ago, when humans were painting animals on cave walls and tracking mammoth herds across frozen tundra. The center of your own galaxy is hidden from you not just by dust and distance, but by time. Now expand the frame one final devastating step. The Milky Way is one galaxy. Current estimates place the total number of galaxies in the observable universe at approximately 2 trillion. 2 trillion galaxies, each containing billions or hundreds of billions of stars, each separated from its neighbors by millions of light-years of intergalactic void. The nearest major galaxy, Andromeda, sits 2.5 million light-years away. At light speed, reaching Andromeda would take 2.5 million years. The most distant observable galaxies lie more than 13 billion light-years away, and the space between us and them is expanding so rapidly that their light will eventually stop reaching us altogether. If crossing the Milky Way is structurally impossible on human timescales, Crossing the intergalactic void is structurally impossible on civilizational timescales, on species timescales, on geological timescales. The gaps between galaxies dwarf the gaps between stars the same way the gaps between stars dwarf the gaps between planets. Each level of cosmic organization introduces another multiplication of distance that pushes travel times from the merely absurd into the genuinely infinite. You cannot cross your own galaxy. You certainly cannot cross the space between galaxies, and you absolutely cannot cross the observable universe, whose edges are already receding from us faster than light due to the expansion of space, placing them permanently and irrevocably beyond reach. The universe is structured in layers of inaccessibility. The solar system is accessible. The nearest stars are theoretically accessible at great cost and over long timescales. The galaxy is inaccessible. Other galaxies are profoundly inaccessible. The far reaches of the observable universe are absolutely inaccessible. And beyond the observable universe, in the regions from which light has not yet had time to reach us, lies a cosmos that is not merely inaccessible but fundamentally unknowable. Each layer contains more space, more stars, more potential worlds, and more distance than the layer before it, and each layer erects a barrier higher than the last. You do not just live in a big universe. You live in a universe that is architecturally designed, at every scale, to keep its contents separated from one another. This is not an accident. It is a consequence of fundamental physics. The universe expanded from a hot, dense state roughly 13.8 billion years ago. That expansion created the distances that now separate galaxies, stars, and star systems. The speed of light, which governs the maximum rate of information transfer and physical travel, was set during the first moments of cosmic history and has remained constant ever since. The combination of cosmic expansion and the light speed limit produces the isolation we observe at every scale. It is not a flaw in the design, it is the design. The universe is not a place built for crossing, it is a place built for containing. Every galaxy, every star system, every planet exists within its own pocket of space-time, connected to its neighbours by distances that function as barriers as effectively as any wall. What does this mean for you? Not for humanity in the abstract, not for hypothetical future civilizations. For you, the person listening to this, the person who looked up at the Milky Way on some clear night and felt a sense of belonging, a sense that this glowing band of stars was somehow yours. It means the galaxy is yours in the way the ocean belongs to a single fish. You can swim in your corner, you can feel the currents, you can sense the vastness extending in every direction, but you will never reach the far shore. You will never see more than an infinitesimal fraction of what the ocean contains. You belong to something enormous and beautiful, and overwhelmingly indifferent to your existence, something that gave you the atoms in your body and the ground beneath your feet, but has no mechanism by which it can ever show you more than the tiniest glimpse of itself. There is a final image that brings this home. On a clear, dark night, far from city lights, the Milky Way stretches across the sky as a luminous river of soft white light. It arches overhead from horizon to horizon, dense near Sagittarius where the galactic centre hides behind curtains of dust, fainter toward the outer edges where the spiral arms thin into scattered star fields. It is one of the most ancient and beautiful sights available to human eyes. Every civilization that has ever existed on Earth has looked up at this same band of light. They named it after milk, after rivers, after roads walked by gods and spirits. They built mythologies around it. They used it to navigate. They painted it on cave walls and wove it into creation stories. It feels close. It feels intimate. It feels, in some profound and wordless way, like it belongs to us. It does not. The light you see when you look at the Milky Way left its sources years, centuries, and millennia ago. Some of the photons entering your eyes tonight have been travelling since before the Roman Empire. Some have been travelling since before the pyramids were built. Some of the faintest glow in the galactic band is the blended light of stars so distant and so numerous that no single one is visible alone. Light that left its sources tens of thousands of years ago, when ice sheets covered half of Europe and our ancestors had not yet planted a single seed. You are not seeing the galaxy. You are seeing a composite of its past, a patchwork of moments stretching back thousands and tens of thousands of years, arriving simultaneously at your retina and creating the illusion of a single, unified, present-tense structure. The Milky Way you see tonight does not exist. It is a ghost image assembled from photons of different ages, a time-lapse exposed across millennia and projected onto the dome of your sky. The real Milky Way, the one that exists right now at this moment, is something no human being has ever seen and no human being ever will. Light does not travel fast enough to show it to you in real time. The galaxy is too wide for its own light to unify it into a single present. This is the final collapse, not just of distance, not just of speed, but of the assumption that the galaxy is a place at all, in the way that a city or a country is a place. A place is somewhere you can be present, somewhere that exists in a unified now. The Milky Way does not have a unified now. Its present is fragmented across 100,000 years of light travel time. Events happening right now on the far side of the galaxy will not be visible from Earth for 1,000 centuries. The galaxy is not a snapshot. It is a time-smeared ribbon of causally disconnected regions, each evolving independently, each ignorant of the others, each separated by gulfs of space-time that no signal and no ship can bridge within any meaningful human time frame. You are inside this ribbon. You are part of it. You are made of it, and you cannot cross it. The most unsettling truth is not that the Milky Way is large, though it is. It is not that the travel times are absurd, though they are. It is that the galaxy you call home, the structure you were born inside, the cosmic address you carry with you from the moment your atoms assembled into a living thing until the moment they scatter back into interstellar space, is so vast that it lies permanently, fundamentally, irrevocably beyond the reach of the species it contains. You will never cross it. Your children will never cross it. Their descendants, 10,000 generations hence, will never cross it. Humanity could survive for 1,000,000 years, 10 million years, 100 million years, and at the end of that unimaginable span, the Milky Way will still be 100,000 light-years wide, and crossing it will still require 100,000 years at a speed nothing with mass can achieve. The galaxy does not shrink, the galaxy does not wait, the galaxy does not care. It simply is. 100,000 light-years of stars and silence, stretching from edge to edge of everything you will ever call home, too wide for your fastest machines, too wide for your boldest ambitions, too wide for your deepest time. You live inside it the way a heartbeat lives inside a lifetime, brief, local, unaware of the enormity it occupies. And tonight, if the sky is clear, you will look up and see it glowing overhead, beautiful and close, and yours. It will feel like something you could touch, something you could cross, something you could know. It will feel like home, and in the deepest, truest, most unforgiving sense of the word it is. A home so vast that you could spend every second of every human life that will ever exist trying to walk from one wall to the other and never make it past the front door.